Right, okay, let's continue with example 4 and example 2 at the end in this part of the video. Okay, so for example 4, to solve this non-homogeneous linear second order ODE. So first of all, as you know, we want to solve for the homogeneous part, i.e. to find the YC, the complementary solution. So we write down the characteristic equation m squared minus 4m plus 3 equals to 0. Then you may want to check the b squared minus 4ac value. Negative 4 squared minus 4 times 1 times 3, 16 minus 12 greater than 0. So you have two distinct real roots. So you can factorize this. So m minus 3 and m minus 1 equals to 0. And then m1 equals to 3 and m2 equals to 1. So your YC is C1 e to the 3x plus C2 e to the x. Right, so we're going to work on the right-hand side of the equation. So your Rx, in this case, is 3 e to 2x plus 4x. So compare this with the standard form of your Rx, where E alpha x and Pn of x. So since in this case, it's a combination of exponential and polynomial of a degree 1 by addition. So you can divide these to two parts. So you can have R1 of x is 3e2x and R2 of x is 4x. So you can propose one particular function for each of these R. So for R1, you can propose yp1 is a e to the 2x, and yp2 is any polynomial at a degree 1, bx plus c, since we already used the a in the first yp. And finally, the yp, proposed yp is yp1 plus yp2, and that is ae to x plus bx plus c. Okay, so then you can work on this yp of, all right, first we need to check whether the yp and yc are linearly dependent or not. So since your alpha is 2 and m1 is 3, m2 is 1, so they are all different, so you don't have to worry about the non-linear dependence, linear dependency of yp and yc. So we can be sure that yc and yp are linearly independent. So we can work on this yp. So we can get dy dx for this yp. So you have 2a e to x plus b, and then you can get the second derivative for a e to x. That's it, right? Yeah. So we can put these values into the original ODE. So original ODE is d2y dx squared minus 4 dy dx plus 3y equal to 3e to x plus 4x. So we put these values in. So d2y dx squared is 4a e to 2x minus 4 times dy dx is 2a e to x plus b plus 3y, so 3 times a e to x plus bx plus c equal to 3e to x plus 4x. And now we're going to compare the coefficient. So we're going to collect all the terms, similar terms together. We collect this e to x, so 4a minus 8a and plus 3a plus the terms with x. So x is just a 3b plus the term without x. So the term without x are negative 4b plus 3c. Then this whole thing equal to 3 e to 2x plus 4x. And then we compare the coefficient. So for e to x, so 4a minus 8a plus 3a is negative a. So negative a equals to 3, thus a is negative 3, and compare the coefficient for x. 3b equals to 4, thus b is 4 over 3. And for this, 4b plus 3c equals to 0, thus c equals to 4 over 3 b, thus 4 over 3 times 4 over 3. So c is 16 over 9. So then you can put this into your particular solution. So yp is a e to x plus bx plus c. So a is negative 3 e to x plus b is 4 over 3 x plus c is 16 over 9. So this is your yp, and thus your y total is yc plus yp, and your yc is c1 e 3x plus c2 e x minus, plus the yp, so the yp here is this whole thing. Yep, that's all for this example number 4. So actually, in this example, this is a graphical representation of the linear superposition for this example number 4 here. So if you see this ODE, it's the same with what is being shown here. So just imagine if you have a system where you put a force onto the mass, and the mass onto a spring. So this spring has a stiffness coefficient K and the damping coefficient C, and the displacement Y as a function of time. So as the independent variable, now it's as a function of t, so dy dt, and here is a function of t as well. So imagine if you have two forces acting simultaneously on the system. So you can model the system using two different equations, but the both equations are a solution to this ODE. Thus you can combine the particular solution. Yp total is equal to yp1 plus yp2, so that is what we have here. So this is just to illustrate to you how the linear superposition or linearly independent solution can be combined into one complete. Okay, so that is for example 4. Next, we're going to do the long example, which is example 2. So this example, we're going to solve it using two methods, using Euler's formula or using alternative method. Okay, so this is our original question. So unlike the other examples, number 1, 3, and 4, so this is a bit tricky because it involves the cos x, and you're going to have to know how to convert that cos x into either Euler formula or you want to use the other alternative option. Okay, so let me go to this example. Okay. Right, so first thing, do the easy one first, i.e. to do the homogeneous part of the solution. So m2 minus 4m plus 5 equal to 0. Then you may want to check the b squared minus 4 is c. Yeah, just do that. Is negative 4 squared minus 4 times 1 times 5. So it's 16 minus 20. Equal to negative 4, so it's less than 0. So you have a complex conjugate roots here. So you have to do completing the square. And minus 2 squared, plus 2. And minus 4 plus 5 equal to 0. So m plus 2 squared plus 1 equals to 0. So m plus 2 squared equals to negative 1. So m plus 2 equal to the square root of negative 1 plus minus. So m1 is negative 2 plus I, and m2 is negative 2 minus I. So these are your m1 and m2. So you can write down your yc. So yc for complex conjugate roots is like the two distinct real roots, c1 e m1 x plus c2 e m2 x. So So you can write it down as C1 e times negative 2 plus I times x plus C2 e times square to the power of negative 2 minus I x. So this is your complementary solution, or you can also write it down in using Euler's formula, where m is equal to negative 2 and your beta is equal to 1. So your yc can be also be written in the form of exponential of negative 2x times a cos x plus b sin x. Okay, so that is your yc. So now the hard part is to work on the non-homogeneous part. Okay, work on the non-homogeneous part. So your Rx is negative, your Rx is e to the minus 2x cos x. I think I'm going to need to start with a clear canvas for this part. So I'm just going to rewrite. Rx is e to the 2x cos x. So compare this with your standard form of Rx, e alpha x Pn of x, but here your alpha is negative 2. Your polynomial, you don't have a polynomial, but your cos x is what you're going to convert it into Euler's formula. So recall Euler's formula, e ix equal to cos x plus I sin x. So cos x is actually the real part of e ix. Okay, so your right hand side equation, the Rx can be written as e to the power of negative 2x times the real part of e ix. However, for convenience purpose, we will omit the real or imaginary term, but so that it will make it easier for us to do. But until now, we can keep it. So here you're going to have negative 2 plus I x. But bear in mind, we're going to only take the real part. So here, okay, it's okay. So your possible yp, is a times e to the power of negative 2 plus I x. But your actual yp is only the real part of your proposed yp. Okay, so the common practice is to neglect the RE or IM, in real or imaginary, in calculation, and only find the final YP actual at the end of your calculation. So the third step is to check the linear dependency of YC and YP. So when you compare the YC that you got previously, it was C1 E negative 2 plus I x plus C2 E negative 2 minus I x. So you can see that this alpha here is the same with this alpha. So these are linearly dependent. So we need to put some treatment to the YP. So we will propose a new YP, which is to put x before the E. So we propose new YP is A times xe negative 2 plus I x as our YP. Okay, so next we determine the coefficient for YP. So we need to do the differentiation. So we want to find out YP dy dx using the YP. Okay, so you differentiate this. So you're gonna have to do this product rule. Plus with put differentiate x, so just 1, so bring everything. So this is your dy dx, and then you do the second derivative, d2y dx squared, and this part here you need to do the product rule again. And this part just differentiate with respect to x. You have And then you can expand this term and try to simplify what you can. So when you expand this term, you will get 3 minus, oh, where, 3. Oh, I think I need to start on the new canvas. So let's continue that on the new canvas. Okay, so what we're doing is we simplify the term. Okay, so when we expand 2 plus I, negative 2 plus I with negative 2 plus I, you will get 4 minus 2I minus 2I plus I squared. And you'll get, so I squared is negative 1, so 4 minus 1 is 3 minus 4I. So then d2y dx squared is 3 minus 4I times ax e negative 2 plus ix plus negative 4 plus 2I ae negative 2 plus ix. Then what we do next is to substitute in our original ODE. So our original ODE is d2y dx squared plus 4 dy dx plus 5y equals to e to x minus cos x. So yeah, just put everything. This term is d2y dx squared. So just put that. So it's a bit tedious actually, this part of the work, and it's easy to make mistake. So you need to be careful here. So plus 4 times dy dx. So previously we have, oh, okay, I hope you can bear with me and still follow. Okay, this is your dy dx, and then plus 5y. So plus 5 times y, so your y is axe negative 2 plus ix. So that will be equal to, e negative 2 x cos x. But then we don't want to write it in this term because we want to make everything is in terms of the Euler form. So equal to e times negative 2 plus ix. Okay. Why is this happening to me? Why? But you got me, right? I hope you do. And then, well, next is you want to compare the coefficient. Okay, so you collect the terms together. You want to collect ax e to the power of negative 2 plus ix. I think I'm going to have to continue in another video because my computer is sabotaging.